but no one knows about them. You have to first collect experience from past mistakes to know and learn from them. So, learning from other people's mistakes, also enabling testing different communication products using the same interface means that black box testing is quite useful there. Penetration testing is quite widely used. There are lots of consultative companies who do penetration testing, and it's also an area where you have to be extremely careful because many of the consultants don't do anything else but review for known errors. So they are doing either manual or automated verification that you are not repeating someone else's products, someone else's problems. So if you, for example, take security scanners, it's a common security tool. What they do is same thing as virus scanners. They look for known fingerprints of problems. And if, for example, a past version of a web server contained a problem, verifying that the version number of the web server is higher than that is not what security testing is about. Security testing is about actually trying out all those inputs that cause problems. And that's not what security scanners are for. Security scanners are administrator tools. Performance testing always finds security problems. There is always a load that will drive the system down. Only solution there is to measure what is that load, be prepared for it, divide the load between servers, just put more iron on the border. Robustness testing as a category is functional testing, so it's actually trying out functional operation of the tool or product, but it's using fault injection principles in actually injecting anomalies within the communication sequence. So communication can be between internal modules, operating system and the software, network, files, hardware, and most commonly users or network. And always when you start analyzing a software or a system, you start from risk analysis. The most open interface you have defines how open your system is. If you are making a web server, it doesn't matter how many firewalls you have in front of it, if they allow web traffic through. So it's as open as all the communication, the most open communication interface you have. Simplifying security testing or robustness testing, you have, for example, if you have a security mechanism like authentication, you have username and password combination that is required to get in. Conformance tests at minimum have to try that your authentication works. Performance testing at minimum is trying repetitions of logins or parallel, how many parallel users you can have at the same time. Negative testing, hopefully in the future, will be more part of conformance testing so that you have verified, you have specified at least a set of negative tests that have to be tried as well. You cannot enter the system by using wrong password, you cannot enter the system using someone else's password, and so on and so on. But when you imagine what all kind of inputs even this simple interface allows, you can imagine how wide the area of robustness testing typically is. You have to try long strings for buffer overflow problems. You have to try different kind of structural modifications. You have to try all special characters that might be used in databases behind the authentication, in files that might be used in some components of the software, and so on and so on. If you analyze different critical interfaces that systems nowadays have, we can start from voice over IP, for example. It's the gateway to traditionally closed critical networks. So if someone is calling over the IP unidentified person towards a critical system on the other end, you are opening traditional closed system through it. Web, always, there are lots of business critical applications running on top of web, internet. LDAP, well, it's quite critical. SNMP, simple network management, was actually one of the issues which made University of Oulu research popular, because everyone has it enabled. It's in everything ranging from network cameras to missiles. VPN connections, encrypted communications. It's still a communication protocol. It might be a tunnel, it might be encryption in different layers, but it's a complex communication protocol, and it's extremely complex communication protocol, meaning it's extremely error prone as well, even from security perspective. Radius, TACACS, authentication, routing protocols, IP protocols, everyone knows about few individual problems like ping of death or so on or so on. But you have all these same problems in all IP stacks, all possible devices implementing IP. It's not just the common operating systems. All network services, the surprisingly complex protocols in industrial automation and so on. Cars have networks inside and so on. All of them are critical, either from openness perspective or being single points of failure within networks. If authentication fails, it means that no one is communicating that day. Measuring test coverage first starts from analyzing those interfaces that you have. Then when you are doing testing, you can use different kind of metrics for code coverage or branch coverage, how many of the security requirements you have verified, and so on. But when you consider the whole input space that can be given to the communication software, you get an infinite space of inputs that can be given. So it requires a new metric, and if someone is interested in researching that, it's a really interesting topic, and there isn't much research on that topic. One basis for starting could be, for example, communication protocol standards. So if you take IETF specified TFTP as a simple example, it's only protocol consisting of 5 elements. You have extremely easy machine-readable format for actually passing it through, to teach it to a test system or script. You can describe it as trees, format of something that you can traverse through and actually generate test cases from it. So even a simple protocol like this builds up a little tree that you can generate all valid cases. You can generate all valid use cases that can be imaginable here. And there are products doing that actually. But it's easy to do. When you add all possible anomalies that you can use in addition to legal values, you get much wider tree already. So even a simple protocol like TFTP typically has in range of hundreds or thousands of test cases for negative testing. But if you imagine a simple protocol like this from brute forcing perspective, if you are breaking a key that consists of this many bytes, how much time does it go to go through all possible combinations, just brute forcing all the possible input combinations to it? So of course you can take a fuzzing way. You can just insert random data. Given enough time, you will cover all the possible combinations, but it will take much more time. So knowing data structures, knowing possible contents to actually find these problems helps a lot. When you decide what was the actual result from the test execution, you get into differences why conformance